Okay, thank you. I'm the last speaker. Then we can go to lunch. I speak a lot. I'm good at ending on time. So, let me get my timer here. I'm going to talk to you about smart objects. We've been hearing a lot about connected objects, and indeed we are moving to a connected world. Everything that we see and do is going to be connected. That's the sign of our times: autonomy, connectivity, and data. And in this conference, you've heard a lot about connectivity and data. This has been actually growing for many years, and in industry, this has been moving for some time. We have many autonomous devices in industry. For example, robotics that can do the work of humans, and we have like smart forklifts. Amazon relies very much on autonomous robotic devices to move their products around, and our airplanes every airplane we fly on can actually take off, fly, and land itself. The pilot is there just to make us feel better. So we are definitely in the age of smart connected objects. And even in our own personal lives, we are now starting to be connected. We have so many products that we use in our everyday life that are smart and connected. And so we're going to see more and more of this happen. And I want to explain to you a little bit about the technology underneath the hood. This is all part of a bigger movement that started about maybe 5 to 10 years ago called the Internet of Things, and you've heard a little bit about that already. It's a huge opportunity, a lot of work going on because of the huge economic benefit that is projected to come out of this, and we're starting to see that. The idea is that very soon we'll have over 50 billion products connected to the Internet. So there's a lot of opportunity and there's a lot of excitement about that. There's a lot of concerns too. But generally, the industry is moving forward in this direction, and we are going along with it. The Internet of Things can be broken down into 3 main components. There's what we call the edge, and the edge is, we call it the edge because it's where the digital world meets the physical world. So it's the edge of the digital world. And the primary function of the edge is to collect data. Over 90% of edge products are actually data collection products. They're sensors and monitors and things like that. And then that data is sent to the telecommunications infrastructure called the backbone, and then that eventually ends up in our server farms that we call the cloud, and then we can do processing on the data to come up with information and insights and make decisions about how to run our manufacturing and cities and agriculture in a more efficient and optimized way. So that's generally how this works. But I want to focus on the edge because that's what we see when we see the Internet of Things. We see the things around us, and I want to talk a little bit about the edge, okay? And in particular, I want to talk about the smart edge, okay? Because actually the edge right now is not that smart. Most of the products that we deploy to collect data, all they do is collect data. That's what they do. But that's all going to be changing very soon. So I'm going to start with describing this in the context of industrial IoT, but then I'm going to move into our everyday lives because that's what I really want to share with you. But because a lot of my expertise is in industrial IoT, I can give you a nice example to start the discussion. So here's where we would expect to see our edge products. In many cases, we are going to install the sensors in our factories, in our farms, in our sewage systems, in our cities, transportation, and so forth. So we can put them installed. We will also have our edge products in autonomous vehicles, drones, for example, trains, robots, boats, and so forth that can collect data for us. And in fact, human beings are part of the edge because we carry data collecting devices on our body, in our phones, and so forth. And so we're going to see workers who wear sensors to help them gauge what's going on and also to collect data on the environment that they're in, for example. So this is what we're seeing. Now, how does this benefit industry? Well, let me give you an example that's a very common example. It's easy to understand, and that is the example of predictive maintenance. So here's a manufacturing plant. You can see there's a lot of equipment on this floor, okay? And a lot of that equipment is moving. There's a lot of motors moving. There are conveyor belts, there's fans, there's blowers, the things are shaking. And that's how a manufacturing facility works. So typically, there may be hundreds or even thousands of motors on a manufacturing floor. If one motor fails, and they have to shut down production to fix that motor, that can represent $1 million a day in lost revenue or lost production. It's very bad to have a failure on a manufacturing floor. Okay, so how do we prevent that from happening? Well, we have to go in, we have to check all the motors. And so I might send a technician to go and check the motors and analyze the motor. And the most common way that we're going to analyze a motor is to listen to it. If you drive a car, how do you know when your car is not right? It sounds funny, right? It vibrates the wrong way, and that's the most common way that we're going to determine if a motor is not working properly. We're going to listen to it. And so we can do vibration analysis. And so we hear this motor sounds normal, but maybe it's not doing that now. Maybe it's doing something different, right? So vibration and acoustic analysis is very important for understanding if a motor needs repair. But actually, and this is like basic technology of about the last maybe 10 years ago. You just look at the waveform, and if it goes out of range, you say, let's fix this motor. So it's a very simple analysis. Just check to see if something is out of range. But motors and machinery are much more complicated than that. What we need is a more sophisticated analysis, and this is another way to do the analysis, where you look at the frequency spectrum on, the vibration spectrum on one axis, you look at how that signal changes over time on another axis, and you look at the intensity on the third axis, and then you get something like this called a spectrogram. What this spectrum might represent, instead of something that sounds like this, it might sound like this. So it's got a more complicated pattern, right? And we need to be able to analyze more complicated patterns, not just a simple vibration. Now, this is actually a pattern of a very high-value machine. And I wonder if you can guess what this pattern is for. This pattern is for a human heartbeat, okay? So this is a very well-understood pattern. And if this pattern changed, if I had this data on your heart and it changed, we would go to the hospital right away because that tells us something is wrong. So a good analysis of vibration or sound can tell you a lot about the health of the machine, in this case, the heart. Now, typically what we're going to do is going to do a very simple, once we have done this, we can very quickly find problems. And what we're looking for, really, is just changes. So if this is my spectrum for my motor, and then this happens, we can immediately see something happened, right? Even without big data and machine, we can quickly, you and I can see, there's something wrong here, right? So when we look for deviations from normal, we have a very powerful tool to do predictive maintenance. So that's sort of the general approach for doing predictive maintenance, is to look for variations from normal. And in a typical system, we'll have our edge device, which is this the gray box, and it talks to a device that sends the data to the server, and then we do our analysis in the cloud. That's typically how it's done. So our edge device is relatively not very smart, right? It just sends the data to the cloud. What we'd like to see, and what we're starting to see, is where we put a lot more intelligence on the front end so that we're not putting all of the work for analyzing data in the cloud. Okay, so a conventional system looks like this. Here's my motors. I have sensors on each motor, and then that sensor takes a waveform data and sends it to the cloud, and then the cloud does all the analysis on every motor, and then it determines whether or not each motor is doing okay, right? That's a lot of bandwidth that I have to send all the way to the cloud just so that my cloud can do the calculation. And for 4 motors, it might be acceptable, but 400 motors, we now have a major bandwidth problem. It would make much more sense to do the analysis, as much of that analysis up front, and then our cloud can just ask, are you okay, right? And because they're smart, they can say, let me do my own analysis Yes, I'm okay, I'm okay, I'm okay. You see, so now our bandwidth is reduced dramatically, and our edge devices can be more autonomous and smarter. And so that's a big push for industrial IoT. Now let's talk about our lives. Okay, so here are our devices, okay? We have smart thermostats and security systems, companions. Even this red device here is a vacuum cleaner that can vacuum your house while you're away, all right? And, you know, maybe I don't want that data to go to the cloud, okay? Maybe I don't really like people to know how often I vacuum my house, right? Or the shape of my house, or, you know, we're going to have smart toilets and things like that. You know, I don't want them to know when I'm using the restroom, you know, that kind of thing. So there's a very good argument for not sending things to the cloud. But we still want the brains. We still want it to be smart. That vacuum cleaner is not going to know my house on the first day. It takes time to learn my house. And that's what machine learning does. It allows you to learn patterns. And usually it's done in the cloud. So instead of doing it in the cloud, let's do it on the device. Let's make those devices smart. Okay? So how do we do that? Now I'm going to give you a very fast course in machine learning. Okay? Because everyone's heard about AI and all this kind of stuff. What is it? And when people talk about it, they talk about it like it's magic, and it's not magic. It does require a lot of computing power. I'll show you that. But there's ways, there's tricks we can take so that we don't need such a big computing resource to do this kind of work. Okay, so here's what we're doing. We're looking for patterns. And generally, we're looking for deviations from normal. We want to know what the normal is. And the way we measure normal is we take a lot of data on normal things, and then we sort of characterize that data. So here's a picture of San Francisco, and the color represents how fast traffic is moving. And red shows there's very slow traffic. And we can compare that to the rest of the map, and we can say, oh, there's something wrong in those red zones, right? There must be a traffic problem in those red zones, right? So this is a classic use of data to analyze what is normal and look for a deviation from normal to identify a possible problem. Okay, so that's generally the basic idea. But a couple of comments I want to make. That data does not have to be perfect. That's something my engineering friends cannot wrap their heads around. It does not have to be perfect. Because when we're doing this type of work, we're using statistical inference to draw conclusions. So even if 10% of the data is wrong, as long as I have enough data, I'll still get the right answer, okay? So, and it doesn't have to be instantaneous. You know, I can collect data maybe once every minute or something like that. So keep that in mind. However, what is important is that we have a lot of it, and we have different varieties of data, okay? So variety and volume is more important than precision, okay, when we're talking about big data and AI. Because in this case, we might conclude there's something wrong, but actually, there's nothing wrong. That's just normal for 5 o'clock traffic, okay? We need more data. We need data on time, not just on position, right? So if we'd measured over several weeks, we notice all the time at 5 o'clock we get that same pattern. So now we have a different type of data that's time is the variable, and it gives us more insight as to what's happening. So it's very important that we have veracity or variety of data when we do these types of things, okay? So keep that in mind. Otherwise, we can easily draw wrong conclusions. Okay, so how does a machine do this? Okay, I'm going to zip through this, but it's really important, but I'm going to kind of simplify everything. There's 3 basic ways to determine, to draw a conclusion from data. There's a procedural approach, and that's the way we've done it for thousands of years. There's correlation-based approach, and there's a mechanism-based approach. And by the way, every time you have a way to draw a conclusion, we call that a model, okay? It's a model, okay? So in a procedural-based model, I open a book, and then it says, if this is happening, do this. If this is happening, do that, and so forth, okay? In a correlation-based model, I look for the way the data scatters, and I can draw a conclusion on that. In a mechanism-based model, well, that's science. That's where we have an actual physical model that is highly predictive, that gives us a prediction. So, for example, let's say I have a procedural-based model, and in my binder, I open up my procedure binder, and it says, is it November? Okay, yes, it's November. Then, in that case, go out and chop down a pine tree, okay? So that's what I do. I go out and chop down a pine tree, okay? That's what I do because I follow the procedure, okay? In a correlation-based model, we notice that people like to chop down pine trees when the weather is colder. So there's this correlation between cold weather and people chopping down pine trees. So we chop down a pine tree whenever the weather is cold, okay? So that's what we do. We go up and chop down a pine tree when the weather is cold. In a mechanism-based model, I have some fundamental mechanism. When the Earth is far away from the sun, that corresponds to winter in the northern hemisphere, and we have a cultural phenomenon called Christmas, and people like to buy trees and decorate them. So I have an actual mechanistic understanding, and now I know I should go chop down a tree during winter, right? So all three of us give predictions, okay? The mechanistic model is the most powerful. It gives us the most precise predictions. It can tell us when Halley's Comet is going to come by the sun to within minutes, okay? But it's the hardest to do, and that's why people like me, we get PhDs in science just so we can build those mechanistic models. But the future is actually in the correlation-based models, okay? Because in correlation, you don't actually have to understand what's happening. You just have to believe it's going to happen again. So if the sun rises every morning, right? I don't have to know about Newton's law of gravity. I just know it has happened every single day. I believe it's going to happen tomorrow, okay? That's induction, okay? That's what we call induction, okay? So machine learning is going to be using induction, okay? Just by looking at the data long enough, you start to see these things happen over and over again. And sometimes we'd like to simplify it a little bit by maybe drawing a line or some mathematical expression that kind of captures that correlation. And that's called abduction. And we might call that a linear regression, for example. Okay? But it's still just correlation, just a way of characterizing a correlation. You don't actually know why it's in a line. Okay, so now, most AI applications that we're seeing are doing a function called classification. We're trying to classify things. Is this a threat? Not a threat. Is this a woman or a man? Is this Mark or Jane? We're classifying things. Is it an apple or an orange, okay? So, for example, here's my home object that's in my home. And it might have a simple procedural, kind of a procedural-based approach. And that's what historically, most smart devices are basically algorithms that are very decision tree type algorithms, very deterministic. So, is it raining? Yes. Don't forget your umbrella. So my companion reminds me to get an umbrella because it's a very simple algorithm. If it's raining, Mark, you should take your umbrella. So as I'm leaving the house, my smart companion says, Mark, don't forget your umbrella, okay? Now we're moving to machine learning-based approach. And so here we have correlations that we've collected over time. And we discover that when it's raining, most of the time people take an umbrella. So maybe over here on the, on the far right, it might correspond to taking an umbrella. But other correlations exist that say, when it's sunny, don't forget your sunscreen, right? And by the way, we're going to get really clever about this. I'll order some for you next time, right? And that's why Amazon is so interested in, in making these smart companions, because they want to help your life, but they also want to sell you things to help you have a nice life too, okay? So that's how we're going with this. Now, classifiers basically are finding clusters. They're finding correlations. And a way to think of correlations is clusters. Okay? We're looking for clusters in data. So here's a classic example of a cluster of data that happens to fall along a line. This is the kind we learn if you had a kind of a good education maybe in high school or college. We call this a linear regression, right? This is a very common type of cluster. And in fact, we try to squeeze everything into a linear regression because it's the only thing that's easy for us to calculate. So you go on Microsoft Excel, it'll do a linear regression for you. So what we're really saying is that there is a cluster that looks like this. That's what we're saying, okay? And that cluster looks kind of like a line, okay? And that's a classifier. We've now classified this data as a certain, type of data. Now, it gets more complicated. You can have arbitrary clusters, right? You can have round clusters, oval clusters, very weird tube-shaped clusters, and so forth. Those are harder for Excel to do. But that's what machine learning can do really well. We can now start to design algorithms that find very unusual shaped clusters. I've shown these pictures as a two-dimensional axis. On the x-axis is one feature, on the y-axis is the second feature. We can wrap our heads around that. But in reality, we're usually talking about dozens or even hundreds of features. That's a highly multidimensional axis. We can't wrap our heads around that. And it gets very, very difficult to find clusters that way. So the data is usually multivariate and doesn't have obvious clusters. So there are algorithms to do that. And I'm not going to get into all of them, but I just want to show you one slide because you hear about this all the time. I want to explain what we're talking about. This idea of deep learning. Okay, you've heard of neural networks. Okay, it sounds like this magical thing, like we made a brain or something like that. Actually, we haven't made a brain. What neural networks is actually it's a way, a relatively simple way, to build a complicated function. Okay, it's like if I said, why don't you chart a sine wave or a cosine wave on this? Well, you would go to your calculator and you can calculate a cosine. It's a kind of interesting function, it's this wave, right? The actual way you calculate a cosine is actually pretty complicated. You've got to do a series of calculations and so forth, but it's all done behind the scenes so we don't know it. So the way you calculate a function is usually some algorithm to calculate a sine wave or a parabola or whatever it is that we're plotting. Now, what if I want a super complicated function of arbitrary size, arbitrary inputs, and arbitrary outputs? That's very difficult to do, but using this approach of neural networks, where we just arbitrarily combine numbers from one point to the next point, we can build an arbitrarily complex function. And that's what we need because we're talking about very complicated shapes. We need an arbitrarily complex function. And that's what this process allows us to do. So there's nothing magical itself in a neural network. What it does, it allows us to build an arbitrarily complex function that we can now use to describe the data. Now, why does this take so much work? It's a simple idea. The reason it takes so much work is because there's a lot of calculations when you do this. And most importantly, where the real work is, we typically want to find that function that best represents the data. That means we have to do an optimization. If I optimize against one variable, that's hard. If I have to optimize against two variables, it's even harder. What if I'm optimizing for 10 parameters or 100 parameters? Then it's extremely a large number of calculations. We have to go to quantum computing, or today we use the cloud because we can have we can have 1,000 computers operating on this. So that's why neural networks, which have been around since the 60s, and they kind of took off in the 80s, and then they kind of died. But now it's here because we finally have the cloud, which gives us the computational power to do that. Okay. Now to train it, you need data. You need good data. And that's where the magic is, because the algorithms themselves have no value because they're all open source. You can get all the same algorithms that IBM uses. You can pretty much download the original research papers and reproduce that. The oil, the gold is in the data sets that are used to train those computers, okay? And that's where everybody is putting their effort. Let's get those labeled data, the training sets, so we can now train our computers to tell the difference between an apple and an orange, to tell them between a happy mark and a sad mark, that type of thing, okay? So maybe you've seen these things where you try to tag your friends on Facebook. Why is Facebook doing that? You are giving Facebook training data. They love it. Thank you for tagging your friends. We now know what your friend looks like, okay? And now I know what a woman looks like because I know a lot about your friend, and now they're labeling that data. So we are giving Facebook lots of value every time we tag ourselves or tag our friends. And Snapchat, when you're putting these, your filters on, Snapchat is learning about you too. So every one of these tech companies is trying to create more and more training data because that's where the value is, okay? Now, it's actually relatively hard to characterize things like people's faces because we have such variety in faces. Everyone's face is different, right? And that's why it requires huge data sets and cloud computing to be able to do it. How can we put that on the edge? Well, guess what? Usually for our objects on the edge, we're not trying to characterize everyone in the universe, we're just trying to characterize me. It's all about me, right? And this is me, by the way, on the right. If it's the same face over and over again, you don't need as big a training set, right? That's actually manageable by a smaller computer, okay? And you can get to a classifier solution much more easily. So if we're talking about objects that have limited purpose, that are trying to understand how Mark is feeling today, then it's easy to collect that data set because it's all about me. And we don't need to have massive, millions and millions of photographs. We just need maybe a few hundred photographs of me, and we can already start to make inferences about Mark, okay? So that's how we can start to imagine things going to the edge. Now, there's other tricks. We're going to use procedural based where it's appropriate to cut down on the computational requirements. We're going to use a mechanism where we know that's available to us, and we'll use the correlation. By combining these strategies together, we can now bring a very complicated, computationally intensive technology to the edge where we have smaller computers, and smaller memory to get smart objects. And so then we can expect things like, here's my GPS, that can give us more contextual information, more useful information. For example, GPS can tell you where to drive, but it can also check your airplane flight. It knows you're going to the airport. It says, hey, your flight's been delayed. You might want to slow down. You don't have to worry so much. Now we can have smart objects. It doesn't have to go to the cloud to do this. Well, it may have to go to the cloud to get the airplane flight, but the brains to do that doesn't have to be on a server somewhere. It can be right there. Or maybe it's noticed I'm driving too long. Hey, how about a break? There's a coffee shop up ahead. That kind of information can be put on locally. It doesn't have to be on the cloud. Or, by the way, this next section road is dangerous. You might want to slow down, play safe. So contextual information now adds to our life, right? It's no longer just here's the route to get there, but I know a little bit about what you're trying to do, Mark. I can help you, okay? And, here's a Cortana on my computer. I come home, she's talking to me. She goes, you're home late, rough day at the office, because over time, she has learned my patterns. She's learned that I usually come home at 6:30, and now I'm coming home at 7:30. This is unusual. What's going on? Maybe I'll put some tea on for you, that type of thing. That'd be nice, because she knows I like tea. And, she can call for pizza. Okay, so this is reality. This is where we're going. And this does not have to happen in the cloud. Now, don't get me wrong, it probably will happen in the clouds because Amazon and Google, who are going to provide these services, have a vested interest in them hosting the data. But it can certainly happen without it being in the cloud. Now, I want to show you something. This is just released by Google. It's actually a really cool video. Google wants this. Everybody wants this. They want to provide this kind of level of service. And here's a chatbot that Google demonstrated where they're literally going to call for pizza on your behalf. In this case, it's actually a hairdresser.
So how can I help you?
Hi, I'm calling to book a women's haircut for a client. I'm looking for something on May 3rd.
Sure, give me 1 second. Sure, what time are you looking for around?
At 12 p.m.
We do not have a 12 p.m. available. The closest we have to that is a 1:15.
Do you have anything between 10 a.m. and 12 p.m.?
Depending on what service she would like. What service is she looking for?
Just a woman's haircut for now.
Okay, we have a 10 o'clock.
10 a.m. is fine.
Okay, what's her first name?
The first name is Lisa.
Okay, perfect. So I will see Lisa at 10 o'clock on May 3rd.
Okay, great. Thanks.
Great. Have a great day. Bye.
So that's pretty amazing, and that's where we're seeing this technology go, so that we are really able to make technology feel a lot more human. Now, don't get me wrong, it's kind of creepy that you're talking to a computer without realizing that, and I think we're going to, as a society, evolve to maybe demand transparency, things like that, and that's another conversation we can have. But in terms of the technology, you can see how the technology can lead to that. So basically, the idea is that our devices now will learn from you and me, not from everyone, but you and me personally, and that makes them more appropriate for helping me in my personal life. So when I talk to Alexa, or Google Home, it may not understand me at first, but the more it listens to me, the more it understands me, all right? It's learning from me, not from everyone, but from me specifically. It can turn, for now, for example, I come home, turns on the heat, but as it learns my patterns, it turns on the heat before I come home, for example. And, who knows what else, Maybe it can detect that I'm not feeling well because my behavior patterns have changed. Maybe it should call my daughter, that kind of thing. So we're going to see a lot of this kind of thing as we go to the edge. Now, finally, I just want to say, this is where we're going, and the technology, I think I've shown you that technology can do it. And you kind of see how it works by just classifying. But we have, as a society, have a huge task in front of us, and it's going to be interesting to see how this plays out. I mean, you remember the movie Her, right? This man falls in love with his computer, right? Because it's a very real thing that can happen. And in fact, we see people who become so excited about the technology. We imagine all these things like companion robots and so forth. I don't know that all of our visions are the correct visions, okay? And the good news is we have a lot of skeptics to remind us of that. And so I think what we're going to see is we're going to see this sort of iteration. You know, we're going to go this way, that way, until we finally settle in on what's the right way to deploy this technology. Thank you.
Merci.